Hello, everybody. I'm Theodore, and I'm talking with Dr. Ben Burningham today. Thanks for taking the time to talk with me.
No problem at all.
So, what do you do in your day-to-day job?
So most of what I do at the moment is split between a few different kind of jobs. One is I spend a lot of time um, developing code, so writing computer programs that attempt to. They're aimed at analyzing data that we gather via various routes on ja- things like giant planets called brown dwarfs. So these are objects that lie in the mass range between stars and planets, and they actually overlap with the mass range of planets as well. Um, and their atmospheres at the low mass end, when they overlap with planets, are very similar to those of giant planets. Um, and so I write codes that try to make sense of that data to tell us things like the temperature of the atmospheres of these atmospheres, the atmospheres of these objects at various pressures, how much of different chemicals there are in those atmospheres, water, methane, ammonia, things like that. And the thing I'm particularly interested in is how to cope with the effects of clouds on those observations. So, and to try and understand the properties of the clouds in the atmospheres. And that's because understanding clouds it turns out, very important for understanding the observations of exoplanets and giant exoplanets. When you look at Jupiter, there's a lot of clouds we can see in the atmosphere, and those have a huge effect on the observations we get of these objects from the ground and from space. But the observations of planets around other stars, giant planets around other stars, are really hard to get in terms of lots of detail because they're either masked out by the brightness of the star, or because when we only observe the planet when it passes in front of the other star. So the data tends to be very hard to do very detailed analysis of. So brown dwarfs, these sort of stand-ins for planets, provide the opportunity to study the same kind of atmosphere in a lot more detail and understand the clouds, and then we can apply that knowledge to exoplanets. So that's most of what I spend my time on at the moment. But I also I work at a university, so I also spend time teaching and supervising students. I supervise two graduate students doing their PhDs at the moment, and that takes time. And I also work a lot in outreach and public engagement, so I also spend time doing that. And every day is a mixture. That's one of the nice things about the job. It's always a mixture of all those things.
So, what techniques do you use to find the compositions of these alien atmospheres?
So the data that we work with for that is what we call spectra. So we've taken the light from these objects, collected it using a telescope, and put it through an instrument called a spectrograph, which breaks it apart and allows you to look at how bright it is at different colors, different wavelengths of light, so different colors of light at different wavelengths of light. And you can look at how bright it is at those different wavelengths. And molecules like water, like carbon dioxide, like methane, they absorb light at particular frequencies. They actually absorb light in a forest of tiny little absorption lines. But those all blend together, so you end up with these huge chunks of color that are completely absorbed or heavily absorbed by these molecules. And that absorption happens for two reasons. Partly because those gases absorb light at particular frequencies, but also because the light that's escaping from one of these objects is being emitted from a hotter part of the atmosphere and coming out through a colder part of the atmosphere. And because of that dynamic of having a hot bit transmitting through a cold bit, you end up with an absorption, so you have less light in those particular frequencies. And that depends on the gases, but also on the thermal structure, on how hot it is at different layers in the atmosphere. So we use those physical principles to understand these spectra, and to try and determine both the um, what's the word I want to use, the abundance, the composition, how much of each, how much water and methane and ammonia there is in the atmosphere, but also what the temperature of those gases is, because then we can try and understand the chemistry. Um, so we use spectroscopy, and we use a lot of computing power to fit all the different, to try out all the different possibilities, and see which ones fit the data best.
So you've mentioned some chemicals like ammonia and water. What do these chemicals mean for the object that you're studying? And what are other chemicals that you're looking for in these alien atmospheres?
Well, one of the things we want to understand is how these objects formed, um, and particularly, because one of the goals is to understand how planetary systems like our own formed. And Jupiter is, the most massive, after the sun, is the most massive object in our solar system, and it's more massive than all the other planets put together, right? And so to um, to understand the formation of all of the whole planetary system, we need to understand Jupiter as a key part of that, and its role as a key influencer of how everything else in the solar system works. And it looks like that's probably true for other solar systems too. That these gas giant planets are really, really important for that. So, if we want to understand the origins and the evolutions of those giant planets, one of the really useful experiments we can do is to see how their composition changes depending on where they exist in their systems, or where we think where we think they formed in their systems. Because when you make a bunch of planets around a star, this is when the solar system would look, we take the example of our solar system, it would look very different to how it does now. The planets were forming out of a disk of gas and dust and rocky material, that was swirling around the young sun, and that the composition of that disk was different depending on how far out from the sun you were, because if you were very close to the sun, that heat of the young sun would boil off, sublime off. In fact, it would take water ice, and boil it out of the solar system, sublime it out of the solar system. So you'd lose water, for example, and other what we call volatile molecules, things that evaporate easily, from the inner solar system. So you end up with a trend in composition in that disk as you go out, driven by that difference in temperature. So you have in the inner disk very little water, and more water as you go out, as a simple example. So the planets that formed from that disk should show compositional variations as a result of where they formed. And so we have theories that suggest how those things should vary. And of course, we want to then test that against observations. So one of the really important ways of testing that is something we call the carbon to oxygen ratio. And that is, as the name suggests, is the ratio of carbon to oxygen in an atmosphere, or in an object as a whole. And we often use that as a kind of measure for where it may have formed in a disk. To measure that in an object like a giant planet, you need to look at the atmosphere, and most of the carbon lives in methane, and most of the oxygen lives in water. So, if you want to measure the carbon to oxygen ratio, you have to be able to measure the methane and water abundance. So that's what those chemicals mean. But there's a bigger picture, because they're not the only places it lives. It also lives in other places. Oxygen also lives in other places. It gets eaten up by minerals that form as dust clouds in these atmospheres. So this brings it back to the clouds that I'm interested in. And it also lives in other places due to chemistry. So you really want to look at all of the molecules you can, and look at their abundances and compare them to the predictions of what you think the chemistry should be doing, if you understand the atmosphere as well as you think you do. And just make what you want to try and make sure with all of these things is that you end up with a kind of a picture that all hangs together, so that you can take these measurements and interpret them in a meaningful way, rather than just measuring carbon and oxygen and then finding out, that it doesn't tell you what you think it was telling you because you didn't understand the chemistry in the atmosphere. So you want to measure as many molecules as possible, and then compare it to what you think you know about chemistry, and see if you know what you think you know about chemistry, really, whether maybe the universe is doing something different again. So the other things we look for are hydrogen sulfide is a molecule that is predicted to be there, that we never see. No one's ever found this in an atmosphere of a brown dwarf via the techniques I use, but it should be there, and we don't really know why we don't see it. So there are things by looking for these different molecules, you kind of create puzzles, and then you try and solve those puzzles.
What are the main observatories that you get your data from, and what observatories are you looking forward to the most in the future?
Right. Yeah. So for what I'm doing at the moment, I've been really using a lot of data that already exists. So I haven't been going to telescopes much for the last couple of years. I use a lot of data from a telescope in Hawaii, up at the top of Mauna Kea, called the Infrared Telescope Facility. It's the NASA Infrared Telescope Facility, IRTF. And it has an instrument, a spectrograph on it called SPECS, and we use a lot of data from SPECS at the moment for this work. But in the past, in my studies of brown dwarfs, I used the United Kingdom Infrared Telescope, which we no longer have a part of, also in Hawaii. The telescopes behind me, on this hill behind me, this is La Silla Observatory in Chile, and the two telescope domes kind of, my finger going to appear? This one here and this one over here. That's the 3.6 meter telescope, which is famous for detecting a lot of exoplanets using its HARPS spectrograph. And the smaller one down the hill is the 3.5 meter New Technology Telescope, which I also used to discover lots of brown dwarfs about a decade ago. We use Spitzer. It's no longer working, but a lot of data from Spitzer gets used in this kind of work, and also a lot of it works with Hubble data as well. I'm not working much with Hubble data myself at the moment, but it's for this kind of work people use a lot of Hubble data. In terms of the things we're looking forward to the most, personally, I'm waiting with bated breath for the JWST, the James Webb Space Telescope, to launch and to start producing amazing science. A lot of my favourite targets are in the guaranteed observations target list, so I know people are going to get data on it, and I'm just keen to see those objects come through. My graduate student, Josephine Gunn, is working on an object called Ross 458c, which is a really fascinating brown dwarf. Well, some people call it a planet. People who study planets call it planet. People who study brown dwarfs call it a brown dwarf. It's orbiting a star called Ross 458, or a binary system, Ross 458 A and B. And it's somewhere on the middle ground of being a brown dwarf or a planet. And there's lots of mysteries about this object that we're trying to uncover, and that's going to be in the first set of observations that JWST takes. So, James Webb is top of my list. But also, not only, but also the Vera Rubin Observatory, which is going to be getting first light in about 2 years, which is carrying out a survey called the Legacy Science Survey. Of space and time, Legacy Survey of Space and Time. That's LSST. I mean, it used to have a different name, but the same initials. And this is an amazing facility. The Vera Rubin Observatory has a telescope which will take an image of the entire sky every 2 or 3 nights. And the idea is to look for how things change. And this is very good for detecting supernovae and other kind of transient things on the sky, things that change. But for the brown dwarfs and the free-floating planets that I'm interested in, it will actually allow us to discover many, many of those by seeing how they move on the sky. So that's going to be super exciting. And then there's 2 space telescopes, one called Euclid and another called, it was called W First. I've forgotten what it's changed its name to. Got named after someone recently, and I've completely forgotten who it got named after. Anyway, W First. They are going to go up sometime in the next 5 to 10 years, and be taking surveys of the whole sky, with spectra of many brown dwarfs. And there's another space telescope called Sphere-X, which is doing the same thing. So there's loads of space telescopes going up in the next 5 or 10 years that we're all super excited about.
Yes, an exciting time.
Yeah.
What are the main struggles in what you do?
Funding. That's one of the biggest things that is a challenge. Is winning money to continue doing it as a job. The UK has quite a restricted funding environment, and so it's very hard for UK astronomers to win grants to support their research. So I collaborate with a lot of Americans who seem to be able to win more money. So every idea I'm working on at the moment is actually working with the exception of my 2 graduate students at Hertfordshire, the University of Hertfordshire. All of the other support that I have for my research is actually via collaborators in the USA. And leaving the European Union is obviously a massive blow to this funding, because most of our funding came via the European Union, or the European Commission, via Horizon 2020 programs, which you can Google. So those, so losing out on that is, or we don't know what's going to happen with that, but the expectation that we'll be missing out on that is the biggest. Brings some big struggles. And then in terms of the actual work, it's problem solving. That's the thing. Is these are complicated things to study. There are many different things to think about, and having an interesting question is obviously a very important first part to any bit of scientific inquiry. But ensuring that your question is actually answerable to some degree with the data that you're getting is the next bit of it. So it's kind of a double challenge to come up with good questions, but also good questions that you can make some progress on, and to come up with good experiments for making that progress. Those are the kind of the intellectual challenges.
So have you and your colleagues found anything interesting in this area?
Oh, so many things. Some of them might even be right. We found lots of. I mean, there's some really interesting things that have just happened. One of my collaborators in the US just discovered, or part of a team. There's a project called Backyard Worlds, which is one of these citizen science projects. You can look it up. And what you can do, I think it's available via the Zooniverse platform of citizen science projects. And what you do with that is help look for Planet 9, which may be there, which is this postulated planet out on the edge of the solar system. It's looking through data from a space mission called WISE, and it's looking for things that are moving on the sky. But alongside the search for Planet 9, people are finding all sorts of really interesting brown dwarfs. And one of the results to come out of this project recently was some brown dwarfs that look unlike anything we've seen before. And we think these are very, very old brown dwarfs that are formed when the galaxy was very, very young and have very little content that's heavier than hydrogen and helium. It makes them look weird. So a collaborator in the USA just discovered 2 or 3 of these, and that's really exciting because that kind of starts to allow us to understand how star and planet formation was proceeding when the galaxy was very, very young. The universe was very, very young, and that's something we haven't been able to look at before. And my student has some really interesting results that are kind of coming together at the moment about this object called Ross 458c and trying to understand whether it is a brown dwarf, whether it formed like a planet around that star system. But it's too early for me to talk about that in public because we're still working on it. So, but in the not too distant future, there may well be some interesting results from that coming out. So that's the most exciting thing at the moment. Yeah.
And to finish us off, what advice would you give to young astronomers?
What advice? Always do what you find interesting. Always work on the things that, spend your time on the things that you find the most interesting. But sometimes, the things that you find most interesting may require some groundwork on things that are not terribly interesting in the first place, and it's worth spending that time to learn things you need to learn in order to do the interesting things, because there's lots of really cool headline stuff in astronomy, like dark energy and exoplanets, and studying clouds in giant planets and brown dwarfs. But a lot of the kind of legwork to get to study those things doesn't seem that interesting in the first place. And for example, studying matrices or linear algebra or things like that at school might seem a bit dull. But if you can get those foundations down really, really well, then it equips you to study the hard things and the interesting things in a way that you can't otherwise. And the other thing I'd say is to have a backup plan. If you're interested in a career in research or doing research or astronomy as a job, which is really fun, it's important to keep your interests diverse, because that, as I mentioned, the funding environment is brutal, and incredibly talented people don't get to work in the field. There's such a mixture of luck and perseverance and talent, all in equal measure, in order to get to the next step each time. And so make sure that you keep your interests broad and varied, so that you can always find the thing that you're enjoying the most, and there's not only one thing that you're enjoying. I think that's the other good advice I'd say, without sounding too bleak.
Thank you for talking to me today.
Cool. Well, thanks for having me.
Hey guys, thanks for checking out this video. Don't forget to like, subscribe, follow me on Instagram at Beginning Astronomy, and look at my website, which is in the description.